Good afternoon, gentlemen. Today is Wednesday, April the 8th, and today we are going to talk about section 14.4, energy in simple harmonic motion. All right, so yesterday we talked about displacement, we talked about acceleration, velocity, and so on. Today we're going to talk about how kinetic and potential energy are used in an object that's undergoing simple harmonic motion. Okay. Again, this is a very long section, and so I'm going to kind of zip through it. Feel free to pause the video at any given point and look at the slide, examine the formulas, make sure that you understand what's going on here. So let's say we have a spring moving horizontally along a frictionless surface. All right. If this represents the equilibrium point 0, and this represents A, and this represents the negative amplitude, and I pull the mass back to the amplitude, the position A, and I release it. Well, at this position A, the energy is purely elastic potential energy. But as the spring draws the block toward the wall, the energy is converted from elastic potential to kinetic. But once it reaches the equilibrium point, as the spring begins to compress, then the energy is again transformed from kinetic to potential. And you can see that in the graph here. This brown line right here represents the total energy of the system. It's constant. It doesn't change because of the law of conservation of energy. But the kinetic energy is going up and then down as the block travels from A to negative A or back or vice versa. And the potential energy is going from maximum to 0 and then back up in terms of its total energy as it goes from A to negative A. So for a mass on a spring, when the object is at rest, the potential energy is maximum, right? And it's at rest, of course, at either end of this diagram. And the kinetic energy is 0. But at the equilibrium position, right here in the middle, this is the equilibrium position, the kinetic energy is at its maximum and the potential energy is 0. Now we know that the formula for potential energy of a mass on a spring is 1/2 times kx squared, where k is the spring constant and x is the displacement from the equilibrium point. Excuse me. And since we know that the kinetic energy is equal to 1/2 mv squared, the total energy is equal to kinetic plus potential, which is equal to 1/2 mv squared plus 1/2 kx squared, at least in this scenario. And I know that that total amount of energy is constant. Now, at the maximum displacement point, we know that all of the energy must be potential energy because the object is not moving, so there's no kinetic. And so at plus or minus the amplitude, we have maximum potential energy, which is 1/2 k times the amplitude squared, because the amplitude is simply the displacement from the equilibrium point. At x equals 0, the equilibrium position, again, right here in the middle in this diagram, the energy is purely kinetic. So the energy at x equals 0 is 1/2 m times v max squared. So because of the law of conservation of energy, the maximum potential energy has to be equal to the maximum kinetic energy. And so if I set these two equations equal to one another and then calculate the value of the maximum velocity, we find that Vmax is equal to the square root of k over m times the amplitude. Seems reasonable enough. All right, examine these two equations up here and you'll come up with this. Now, the reason that we calculate this Vmax value is that earlier in the last section, we calculated a Vmax value of 2 pi times the frequency times the amplitude. Now, if I take these two terms and set them equal to one another, notice I can cancel out the amplitude. The amplitude plays no role here. And if I use that, I can actually rearrange that equation to calculate the value of the frequency. And so the frequency in the period of simple harmonic motion are determined by physical properties of the oscillator. The frequency and the period of the simple harmonic motion do not depend on the amplitude. In other words, it doesn't matter how far back you draw that mass on the spring, it's still going to vibrate with the same frequency. All right. So the frequency is equal to 1/2 over 2 pi. 1 over 2 pi times the square root of the spring constant over the mass. All right. I'm not going to read through this entire box, but again, feel free to pause the video and have a look at it. It's essentially just a summary of what we just talked about. Whoops. Okay. So let's do an example problem. A spring has an unstretched length of 10.0 centimeters. All right, so that's this distance right here. A 25-gram mass is hung from the spring. So don't forget, we got to convert that to kilograms. Stretching it to a length of 15. Gosh darn it. 15. So in other words, the change in the length of the spring is 5 centimeters. And again, we got to convert that to meters. Now, if the mass is pulled down to that 5 centimeters and released so that it oscillates, what will be the frequency of the oscillation? All right, seems reasonably straightforward, right? We've got our delta L value. And so what else do we need? Well, turns out that we have to calculate the spring constant first, but let's read through this. The spring provides a linear restoring force, and so the motion will be simple harmonic. The oscillation frequency depends on the spring constant, which we can determine from the stretch of the spring. All right, and that's what we'll do in the next slide. So here, when the mass hangs at rest, after stretching the spring to 15 centimeters, the net force must be 0. Therefore, the magnitude of the upward spring force equals the downward weight. So K times delta L must equal M times G. And if I rearrange this to solve for the spring constant, I get mg over L, and plugging and chugging here, that gives me 4.9 newtons per meter as my spring constant. Now, we're not finished. We got to keep moving here, because we're just calculating the spring constant in order to calculate the frequency. Now we can use the formula for frequency, 1 over 2 pi times the square root of K over M, and that gives me 2.2 hertz. All right, 2.2 hertz as the frequency of this particular block on a spring. So 2.2 hertz is 2.2 oscillations per second. This seems like a reasonable frequency for a mass on a spring. All right. All right. Now, my friends, that brings us to the end of section 14.4. Your homework for tonight is to do questions 17 to 24 at the end of chapter 14 in your textbooks. This is the last lesson. You are going on vacation, so enjoy the rest of Holy Week. Have a happy and blessed Easter, and enjoy your spring break next week. I will be back on April 20th with the next lesson. So in the meantime, take care and be well.